Today's code for the class is 7352. Today's code for the class is 7352. So we've been seeing elimination reactions, substitution reactions, and here I want to summarize how can you decide if the reaction is going to go through an elimination reaction or a substitution reaction. But honestly, the best way to learn how to do this is to do a lot of problems, see a lot of different bases, a lot of different nucleophiles, and familiarize yourself with all of these reactions and reagents. So remember that E2 mechanisms are the ones that happen with strong bases, that it's more likely to happen in tertiary alkyl halides, and it's very useful. E1 on the other side is much less useful because it will give us a mixture of E1 and SN1 because it will go through the carbocation, and then now the nucleophile or the base, remember that those two usually go together, right? So a base can act as a nucleophile and a nucleophile usually can act as a base, and so they both can come, grab a proton and do an elimination, or they can come and attach or attack the carbocation in the center or the carbocation and form a SN reaction, right? So E1 and SN1 reactions are not so useful as E2 and SN2. So the best way to figure out what type of reaction we're seeing is to look at the nucleophile or the base. And so when we have strong nucleophiles or strong bases, we're going to have these reactions that you're seeing. For a primary, we'll get major SN2. For a secondary, we will get E2. And for a tertiary, we're most likely going to get E2. And now for weak bases and weak nucleophiles, it gets a little more complicated. So here you have a summary of everything that could happen, right? So the only thing that you can get from here is probably just eliminate the ones that are never going to happen. So for example, with a weak base or a weak nucleophile, you're never going to have an an E2 reaction on a tertiary alkyl halide, right? So that's something that you can get from here. So when does the SN1, SN2, E1, or E2 happen? So good nucleophiles that are weak bases, they will favor substitution. And why is that? Well, these molecules right here, right, they are all good nucleophiles because they have a negative charge, and you know that that is preferred. Now, they are not good bases because they are stable. So these as bases are quite stable because look, iodine is large, so it can stabilize the electrons. The same with bromine, the same with sulfur. Carbon, it can resonate with the nitrogen, and this one also has resonance because the carbonyl on the acetate allows it to resonate. So these are stronger nucleophiles than they are bases. So these will favor substitution over elimination. Now, on the contrary, we have bulky bases that they are not nucleophilic. So that will be terbutoxide, potassium terbutoxide that we've seen over and over. So remember, we have a negative charge right there with the plus. So remember we said that this was not a good nucleophile because it's so large that it cannot go and reach for the electrophile. But it could go and get that hydrogen because it's not very substituted. So they are large to go and do a substitution, but they can remove that small proton. Remember, the DBU and DBN, those are nitrogen-based bases. And so here is again, with strong bases, the elimination will occur in an E2 mechanism, right? Because the strong base will come and get one of those hydrogens, right, in this case, and that will give us the E2 product. But with a weak base, the Br first will leave, and then we can get either the SN1 or the E1, right? Because we allow the formation of that tertiary carbocation, and then water can act as a nucleophile or as a base. It's weak in both cases, but it can act as both. With strong nucleophiles, we will have an SN2, right? We've seen that. That's a very strong nucleophile. And with strong bulky base, we will not get an elimination because this is too large to go and reach for the electrophile, but it could come and reach for the beta hydrogen and give us the elimination product. So here with the strong bases and nucleophiles, we will get a mixture. So water is both strong base and nucleophile. So in this case, in the case of secondary alkyl halides, we could get a mixture of both of them. It could either come and abstract the beta hydrogen and give us the elimination product, but it could also come and attack the electrophile and give us the Br. So for secondary alkyl halides, we will get a mixture. When we have a strong bulky base, only eliminations are going to happen because remember that potassium tetrohydroxide cannot come and reach for that electrophile. And with weak electrophiles, so what's going to happen is that we're going to get a E1 or SN1 type of reaction, right? So we're allowing that Br to leave to form the carbocation, and now water could come and either do a substitution reaction by attacking the electrophile or an elimination reaction by attacking the beta hydrogen. So here I'm gonna post these. You have a couple more summaries that go over everything that I just said. So here is one and here is another one. So they all say basically the same. And as I said, this can get overwhelming, but as you practice more and more, you'll see that this becomes more intuitive because you're going to start recognizing bases, recognizing nucleophiles, and that will allow you to know if the reaction is going to go through an SN1, SN2, E1, or E2.